would love to know, like with the advent of all kinds of computer things and AI and whatnot, exactly like what you'd have to do here. But television camera is at ground level here. It is filming the liftoff of a space shuttle that is rising vertically according to the position equation S equals 50t squared. So they are giving us this equation for the distance that shuttle has traveled. So somebody somewhere has figured out how that distance is changing. S is measured in feet and T is measured in seconds. The camera is 2,000 feet from the launch pad. Find the rate of change in the angle of elevation of the camera shown in the figure to the right at 10 seconds after liftoff. So, I would love to know, because whenever you film something like this, is there a person at the camera filming it? Because, if you ever tried to film things that are moving, like if I ever try to film like the kids playing ball or something, it's not very easy to do. Because they're all over the place and you're trying to follow them, and if you watch it here, you can't see, the game good, but then you get off. So, I don't know if they have a person, or it could be just sort of like programmed. I mean, this day and age, it could be like sensors that it's like, watching. I don't know. AI might be running the thing. I don't know. But your camera angle is not going to be just like a constant rate camera angle, because of the effects of gravity, you are seeing, this is changing at a rate of 50t squared. We know that's a parabola, so it's going to change fast at first, and it's going to kind of slow down to a certain point. So we're not looking at a constant rate that camera angle is changing. So we need to know about like the rate of change of that camera angle. Perhaps it's like programmed ahead of time to, follow this correctly, just based on what you know is going to happen. Maybe there's a person behind it just doing their best. I don't know, but I'm pretty sure if it's a big shuttle launch and you're the guy behind the camera and you get behind, then you're going to be disappointing a lot of people there. In this case, we're still dealing with the right triangle, but are we doing, in this right triangle, are we doing Pythagorean theorem anymore? We've only got one side. We know about this side. We care about this side, but we don't know what it is, right? That value is changing. And we care about the angle. So what with right triangles are we going to have to use that's not Pythagorean theorem? We got to use some trick. Specifically, which one? This is going to be sine, cosine, tangent. Which one are we going to use here? This side right here would be our opposite side. This side right here is our adjacent side. Which trig function is opposite over adjacent? So, opposite over adjacent is tangent, right? So we're going to say tangent of theta equals the opposite side, which is S, over, now for my steps that I've got here, I could use like A for adjacent, or we're thinking a little ahead here, is that bottom distance changing at all? We could go ahead and throw a 2,000 in there, or my steps that I've got laid out here has us throwing it in a little bit later, so I'm going to do that here. Identify variables from the equation, determine if the quantities are constant or changing. So constant, we have A, which is 2,000 feet. Do we have anything else in this problem that is constant? Do they give us a rate? Okay. That gives us S. It does not give us the rate that S is changing. That would be ds dt. And it's actually not going to be constant in this particular case. So, so most of the problems we've had have given us a constant rate. This one actually doesn't. Okay, so it's going to have a little twist to it. Now, changing, we know that both the angle and the value of S are changing. And then we need to think about what we are supposed to find. The problem says to find the rate of change in the angle. What's that going to be? D what dt? D theta dt. The rate of change in the angle of elevation of the camera, shown in the figure to the right, at t equals 10 seconds. So d theta dt when t equals 10. Okay, so we want to plug in any constants that we can into this equation, right? So we've got tangent of theta is going to equal S over 2,000. Right there. And so we do not need to switch this to only one variable because I really should change that to say two variables because you have like one variable on each side is really what I'm meaning there. Sometimes they're on the same side though. But we've just got two variables here. We are good to go on that part. We can go ahead and take the derivative here. So if we take the derivative, what is our derivative of tangent? Secant squared. So we're going to have secant squared theta. What do I need with that? D theta dt is going to equal S over 2,000 is really just 1 over 2,000 times S, right? So when I take the derivative of 1 over 2,000 times S, I just get 1 over 2,000. But what do I need with that? ds dt. We can. Because when we start to look at this, I don't have anything I can plug in. Nothing, right? Because I got a t equals 10, but there is no t in this problem. I am trying to find d theta dt, so I don't want to replace d theta dt, right? I don't want to replace that one anyway. And I need to know theta, which they also don't give me, right? So this one is tricky. Most of the ones that we've done so far have been easy once you get to taking the derivative part. This one's tricky because there's a lot of stuff we're going to have to figure out. So, as Connor suggested, I know that S equals 50t squared. So, if I need ds dt, I could take the derivative of of S. So, ds dt is going to equal 100t. And this is the only time this has happened to us. We're taking the derivative of t with respect to t. We do not have to put dt here because that would be 1, right? And you could if you want, but it's just going to be 1. It doesn't change anything. Now, I need to know ds dt. We're looking for when t equals 10, right? So if I want to find ds dt when t equals 10. So that's going to be 100 times 10, which is going to give me 1,000. So right there for my ds dt, I'm going to have 1,000. I know d theta dt stays there. That's what I'm trying to solve for, so I don't have to replace it. But I also don't know theta. What am I going to have to do to find theta? I don't know enough sides, and Pythagorean theorem won't give me an angle because it will just, Pythagorean theorem is just the sides, right? A squared plus B squared equals C squared is only the sides. There. Now you could maybe employ it a little bit later, but we definitely have to do something else first. So like what I know so far, if I think about the triangle, I know that theta is right here. I know this side right here is 2,000. Now if I had one more side, I could find theta. I could use some inverse trick to find theta. How could I find one more side? What did they label this side on the picture, that vertical piece right there? They labeled it S. Do we have any way of finding S? We can plug in the value for T because we know that S equals 50 T squared, and we know T is 10, right? So that is 50 times 100, which will give us 5,000. So at this moment, S is 5,000. So now, at this point, we're going to use the calculator, so I am not going to do Pythagorean theorem and, like, secant is 1 over cosine. Like, I'm not going to do that necessarily. I am going to find my angle for theta. Okay, so to do that, I'm going to say tangent of theta equals 5,000 over 2,000. And then how do I get rid of a tangent? What's the inverse of a tangent? The way I worded it, like, kind of gives it, tangent with the negative one, it's the inverse tangent, right? It's like you do just call the inverse of tangent inverse tangent. So we're doing inverse tangent here, and we're going to use the calculator for this. If they gave you unit circle values, it wouldn't necessarily have to be a calculator problem, but we don't have unit circle values here, so let's pull up Desmos. And we are going to do tangent inverse of 5,000 over 2,000. I think, yeah, we're in radians. You want to be in radians. So we are getting 1.19. Remember, that's radians, not degrees, so that's a reasonable answer, right? Like, so 1.19028. You might want to keep that whole thing. So theta is going to be 1.19028, and so on. All right, so we can plug that in. What else I forgot right here? So secant squared of 1.190 here. Okay, so now we actually can solve this from this point. We've plugged in numbers for everything. So I have secant squared of 1.190, we'll keep that whole decimal, d theta dt equals 1 over 2,000 times 1,000 is really just 1/2 right there. I'm just going to type the secant in. I think Desmos does secant squared correctly. Let's check it. Okay, it worked. So I've got 7.249 repeating. I bet that's 7.25 exactly. But we'll just copy and paste. And then we just need to divide both sides by that. number there, and if we do 1/2 divided by this number, we are getting d theta dt is going to equal 0.069. What are our units for that? What would theta be measured in? It's an angle. How do we measure angles? We only have two options, degrees or radians. We're using radians because I got the calculator in radian mode, and everything on the AP exam is always radians. Your book may have a degree problem just because they put some different stuff in there. We could do this in degrees, but we would just need the calculator to be in degree mode. And then, what is the unit of time that we were plugging in? Seconds. So, at that 10-second value, the camera should be, angle should be increasing at a rate of 0.069 radians per second. So, that one's a little tough because you got to do so much work to find the things that you plug in after, I think. But I think it's a good problem. Alright, let's keep going. These problems, I love it. Like, it kind of explains to me sort of like how radar is like working. Now, if you are in this little building working the radar machine, it probably just tells you how fast the plane is going, how far away it is, those sort of things, right? But somebody, number one, had to create that radar, like figure out how this was working, and understand how to make these calculations at some point. And somebody somewhere like programs these machines to do the right thing. So somebody's using it. Probably not a lot of somebodies, right? There's probably not too many people who have the job of designing or programming radar equipment. Pretty cool job. But I think it's cool to like know a little bit about how it works. So whenever the radar is like sending out its signal, I wish I could explain this in better terms, but sends out its signal. That signal goes out. The signal is the S on this picture right here, right? It goes out. It does whatever the signal does, bounces back to the plane. However, this magic happens right here that I wish I understood in greater detail. Goes, bounces off, comes back. The radar is able to measure the distance from the radar machine to the plane and make calculations based on what it sees happening, how that's changing, right? So what we see with the S, much like our radar gun for the police officer, is that S is not the calculation of the plane's speed unless the plane is on this path, like dive bombing into the radar station, right? The plane should be flying across the radar station. So if we want to know how fast that plane is going, we need to see how fast X is changing. But what we're going to be given from the calculations of the radar is how fast S is changing, right? And we have to put that into context. So we have this scenario. The airplane is flying on a flight path that will take it directly over a radar tracking station as shown. If S is decreasing at a rate of 400 miles per hour. So like my radar equipment can tell S is changing at a rate of 400 miles per hour. But S is not the speed of the plane, right? What is the speed of the plane is what we care about. So, our equation here, what equation are we going to use? We've got a right triangle. If you have a right triangle, you're pretty much going to use Pythagorean theorem or trig. If you're using trig, you need angles. Do we have any angles here? We do not. So Pythagorean theorem is what we're looking at. So just because of the way I've set up my steps, I'm going to say a squared plus x squared equals s squared. But which term is constant there? That a is always 6 because our plane is flying at a steady altitude, right? So if you want to go ahead and plug it in right away, like I would expect you to be working towards like where you're not writing step 1, step 2, step 3, step 4. You're just kind of going through the motions there. So if you wanted to go ahead and plug in 6 right here, that'd be fine. What is changing? Well, actually, there's one more thing that's constant. What else is constant? It's a rate. ds dt. And so ds dt is decreasing at a rate of 400 miles per hour. So we need negative 400 miles per hour. So a is constant. What about x and s? Are they constant or are they changing? Both of those are changing. As the plane moves this direction, the x changes and s also changes. So x and s are both changing. We need to think about what we're trying to find. Okay? It says, what is the speed of the plane? So the plane is moving this direction. What is the speed of the plane as far as like our equation goes here? It's a speed. A speed is like a rate of change, right? So it's got to be either dA dt, dx dt, ds dt. Which one is it going to be? It is dx dt because it is the rate at which this side right here is changing. That's the path the plane is moving along, right? So that is the speed of the plane. So it's dx dt, but because they use the word speed instead of velocity, we want some absolute value bars here. If we get a negative, we're going to change it to a positive at the end, right? And we want this when s equals 10 miles. Okay, so we're going to plug any constants that we have in. So a can be plugged in. We've got 6 squared plus x squared equals s squared. We do not need to change this one to a single variable because we already just have our 2 variables here, right? So we don't have to, if you have 3 variables, then one of them is probably going to have to be changed, or they have to give you a lot more information for the problem, right? And we don't have that here, so we don't have to do that step. We were going to take the derivative. Derivative of 6 squared is 0. Derivative of x squared is 2x dx dt. Not a plus sign, an equal sign right there. Derivative of s squared is 2s ds dt. Now we want to plug in the things that we know. Dx dt is what we're trying to find, so it does not get replaced. I know s is 10. I know ds dt, so I know s is 10. I know ds dt is negative 400. What am I missing? What do I not know? I do not know x. So a lot like the last problem, we got to find x, but it's a little easier to find x this time because at the instant that I'm concerned with, I know that my altitude is 6. I know that s is 10. I want to find x right here, so I can just do Pythagorean theorem, right? X squared plus 6 squared equals 10 squared, so x squared plus 36 equals 100. So x squared is going to equal 64 whenever you subtract that 36 from both sides, and we will square root. You can tell this is definitely a textbook problem because they've given us something that comes out to a whole number. In real life, unlikely that that happens to us. But they might do it to you on the exam just because they're wanting you to know how to set it up without a calculator. So now we've got x right here as well. And, oh wait, oh gosh, that was a mistake. There we go. So now we know what x is, and we can just plug everything in. We should be able to solve pretty easily from here. So we've got 2 times 8 dx dt is what we're solving for, so we do not need to plug that in. We got 2 times 10 times, what was that one? Negative 400. Okay, so we've got 16 dx dt is going to equal, let's see, gracious, we got negative h with 3 zeros, 8,000, is that right? Yeah, and then we need to divide both sides by 16. And if I'm doing this without a calculator, because they might give this to you calculator inactive since they gave you nice numbers. So, like, that's going to be negative 500. I think you're right. Because it would be like a half of 1,000. Because, yeah. Because 1,600, yeah. So it's going to be negative 500. That'll be miles per hour. But, exactly, because they asked us for speed, we will get 500 miles per hour. If they wanted velocity, we'd have a negative there. Okay, you very likely will see a like some sort of Pythagorean theorem problem. They could give it to you in a lot of different contexts. It's particularly helpful if they give you the picture because that helps you realize you're dealing with Pythagorean theorem. Sometimes if they describe it in words, it's really hard to tell what they're looking at. Our book does give us pictures for most of these. All right, let's keep going. Okay, so does anybody in here work on cars some? I know that probably Kendall gave a look like, yeah, I'm a mechanic. Anybody work on cars sometimes? So I think it is helpful in this to understand how a 4-stroke engine works a little bit, to understand like what this picture is even doing. Plus I think it's probably just a good thing in general because probably the majority of us, anybody have an electric car? No, you have an electric car? Okay, so y'all have one. But most of the time we are driving something that has a 4-stroke engine in it, right? Also, I was asking, if any of you work on cars and are available, I think we're going to keep the van and get it fixed. So I thought got somebody that's going to do it. It's good to know a little about how things work. Even if you're not going to actually do any work on your motor yourself, which I wouldn't really. Oh, good gracious. Okay, here is, I didn't realize this had such music with it. Okay.
A basic lesson in the fundamentals of a 4-stroke EFI gas engine may be helpful to your understanding of Mercury products. Here are the basic components of every 4-stroke gas engine: a piston, a connecting rod, a crankshaft. As the piston travels up and down in the cylinder, this lateral motion is turned into a rotating motion at the crankshaft. The longer the stroke of the piston, the larger the displacement of gas and air occurs in the cylinder. To propel that piston, we need to ignite a tiny bit of gas and a whole lot of air. This creates expansion inside the cylinder. The fuel delivery system consists of an air intake manifold, valves, intake and exhaust, a fuel injector, and a spark plug. A 4-stroke engine is called a 4-stroke because 4 up and down motions are needed to complete the cycle. In the first stroke, the The piston travels downward as the intake valve opens and a mixture of air from the atmosphere and a metered amount of gas from the electronic fuel injector enter the cylinder. This is called the intake stroke. On the second stroke, the piston travels upward, compressing the air and fuel to make a highly combustible mixture. This is called the compression stroke. At this point, the spark plug fires, sending the piston downward from the expansion of the air and gas mixture. This is the combustion stroke. The fourth stroke is the exhaust stroke. As the piston travels upward, the exhaust valve opens to release the burned air-fuel mixture. When the piston reaches the top of this stroke, the intake valve opens and the cycle begins all over again. It takes one up and down motion, or 2 strokes of the piston, to create 1 revolution of the crankshaft. RPMs, or revolutions per minute, is how many times the crankshaft rotates within that minute. At wide open throttle, the crankshaft may turn at 5,000 RPMs, or a dizzyingly 83 times per second. Meanwhile, the piston traveled up and down 166 times in that same second. Want to see how fast that is? Now, that's fast. Let's see it again. Amazingly, the 4-stroke EFI engine does this smoothly, quietly, and reliably for years and years of operation.
So, I feel like that is a very informative video. And they have picked the perfect voice to do it. I feel confident that that man knows what he... Yeah. Yeah. He sounds like a man that really enjoys telling somebody about how a 4-stroke engine works. I think that it is very informative and fascinating. Think about that when you're driving home today. Like, you know, most of you probably have like a 4-cylinder or 6-cylinder engine. So you have 4 or 6, or if you got like a big engine, you got like 8 of those. 8 of those are in your car, and every one of them is doing that 100. If you're going 5,000 RPMs, 166 times per second in every one of those, and that is really fast. And then all of that is converted, to the spinning of the crankshaft that makes, everything else spin, and then your wheels spin, and then you go. And everything is super fast. And your car does that over and over and over and over again all day, every day for long distances. And amazingly doesn't break, right? For most of the time. So your car, bless its heart, it was working really hard, Jericho. Life was rough for it, and it just couldn't take it anymore. My car, it was doing it fine in the deer woods and practice. But I think this is fascinating to see. So, in this case, we have a piston here. They've turned the picture on its side. Our video was vertical, depending on what type of engine you have. I don't even know which direction they're in. I couldn't even tell you. Vertical, yeah. I don't know why we made this one horizontal. Okay. So this one's that, right? So what we've got here is both of these rods right here are fixed, and I have forgotten which ones were which. But this rod right here has a length of 3 inches. And then this rod right here has a length of 7 inches. And those things do not change, right? Because they are metal rods that if the length of those rods do change, your car's not working anymore, right? Because it's very precise there. So this distance right here is going to change, right? Because this piston is going up and down, or left and right in this picture, right? back and forth really, really fast. So, I barely understand how the engine works itself. I certainly have never designed an engine. But I imagine that this could possibly be something that you want to analyze, particularly if a car company is building a new engine, right? Because you're talking about building an engine that costs a lot of money to make. The engine itself is going to cost a lot of money, but if you're the company making it, you're going to have new machinery to make the engine with, which is going to cost thousands and thousands and probably millions of dollars. Then you have to be able to produce this engine at a rate. You want to make sure in every aspect that this thing's going to work, right? That is why we have, mechanical engineers, because you cannot spend millions of dollars on machinery to make a motor that is not going to make it very long because you didn't run the calculations correctly. So I have no idea to what extent they actually run all of this stuff, because I obviously have not been in that world. But I am certain that somewhere somebody is running a lot of numbers on different engine designs if they're changing things or if they're making adjustments. So it makes sense to me how this question could come into play, right? Like, there's going to be a lot of things you got to consider here. But in this case, we are going to look at this particular case. We have the 7-inch. This one's the connecting rod. It's fastened to the crank. This is the crank right here of 3 inches. The crank shaft rotates counterclockwise at a constant rate of 200 revolutions per minute. Find the velocity of the piston when theta equals pi over 3. Okay, so the velocity of the piston, we got to keep in mind the piston is connected to this right here, right? And so that piston is going up and down, or left and right in this particular picture, back and forth. So we're supposed to find the velocity of the piston. What is that going to be for whatever equation we start coming up with? Is dx dt. That's what we're looking for. Okay, so I'm a step ahead because we haven't written our equation yet, but that's what we're trying to find. All right, so I need to write an equation for this. I see a triangle. I've left some hints here for the triangle stuff. I'm not sure they're so applicable to this. Can I use trig, regular trig, right triangle trig? Is this the right triangle? No, it's going to be a couple times, like at certain points, but most of the time it's not a right triangle. I cannot use right triangle trig. Can I use Pythagorean theorem? No, same reason. Pythagorean theorem is only for right triangles, and this is not a right triangle. Okay, I cannot use that. I can't use similar triangles like we did with the cone stuff because I only have one triangle, right? So no similar triangles. The cone, like where we set up that ratio, like radius over height equals, like whatever the radius of that was over the height. Yes, yeah, where we had to like change that. So we did use a little bit similar. They weren't really similar triangles. They were similar cones. But triangles would work the same way for that. We can't do similar triangles because to do similar triangles, you've got to have 2 triangles that are similar. And we don't have that here. We're going to see one of those in a minute. Ideas. What can we do if we got a triangle that's not a right triangle?
You can set theta equal to maybe like pi over 2, and then that would make it a right triangle. And use the Pythagorean theorem to find x then. At those points.
The problem with that is it only gives us the answer at one point. And it's not even the point they're asking us about because they're telling us theta is pi over 3, which is the point that we're looking at. So while it would work for that one particular point, at pi over 2, or you could even do 3 pi over 2. It's not going to work at other points. And now that I'm saying this, I don't know if you've ever done what we need to do. I think it's gone. I don't know that you did it in Math 2. It's not in the curriculum in Math 2. We used to sometimes still do it. Have you guys ever done the law of sines and cosines? Did we do that? We didn't do that in pre-cal, did we? I don't think we did. Okay. All right, so I need to talk to Ms. Swisher about putting this back into Math 2 because I just don't have time in pre-cal to get to it. There's too many other things. I don't think you have. Yeah. We need to work. We need as a math department, we need to work this back into the curriculum, even though it's not there. Especially if you saw it on the ACT. It's not hard. Well, there's parts of it that can be hard, but it is in pre-cal, but it's in Unit 4. And Unit 4 is not on the test. And we didn't do Unit 4. It was like the after the exam. Actually, I don't even think with your class we did the after the exam stuff. Because it was only like 4 days and we just did a Desmos project, didn't we? Yeah. Actually, Polars 3, we were like, that was on the test, so we barely did 3. We made it, though. We were fine. But we need to work this one back in, because you haven't seen this. So that would definitely explain why we don't know what to do here. We might try to do some warm-ups with this stuff, because it might be something that you run into in some other classes in college, perhaps in like some physics classes or some like your beyond math, Calc 1 classes might just expect you to know it, but it's honestly not in our curriculum anymore, except for in Unit 4 of pre-cal that's not on the test that we didn't have time for. It might be the thing I need to bring back in after the test, really. Law of cosines is the one that we need here. You wouldn't know that because you have never been taught this. The law of cosines is this. So like if this is angle A, this is angle B, and this is angle C. Okay? Then we will label the side across from the angle with the lowercase letter that matches that angle. So for example, capital A, we would label this side lowercase a. Capital B is here, so we would label the side across from capital B with lowercase b. And we would label capital C here, we'd put lowercase c here. So, law of cosines, it's really so cool and helpful. Law of cosines is that a squared equals b squared plus c squared. Pretty sure it's a 2 right here. I may have to go look this up. 2bc cosine of a. Let me double check that. A quick little search right here.
I remember seeing this in ACT.
Yeah. Yeah. Yeah, that's it. I got it right. It's been a while since I've taught it. It used to be in Math 2. They took it, when they redid Math 2, which was several years ago. They just made some slight adjustments to Math 2. They took it out where it's not required anymore. We used to teach it in with regular trig. So what law of sines and cosines are more complicated, but they work for all triangles, not just right triangles. Okay? So this is what we're going to use. Okay? And in this case, this is A, this is lowercase a. This would be B, this would be lowercase b. This would be C, this would be lowercase c. So this is the formula that we're going to use. And it looks really complicated, but the good news is that we've got a lot of constants in this one, right? Because when we're identifying our constants, in fact, actually, I'm going to change that B right there. I am going to change the b. The b in our picture is really x, so I'm gonna change my b. I'm gonna change it to an x. Change this to an x. I'm gonna change this to an x. Right, only because that b is an x in this picture. All right, so my constants in this graph are that A, which is the connecting rod right here, always has a length of 7 inches. And the C, which is the crankshaft right here, always has a length of 3 inches. Okay, changing our x value is changing. And in this case, we actually could probably change this right here too, if we wanted. They label this angle right here as theta. Right now, in this formula, it's A. Let's go ahead and change it to theta so it matches the picture that they gave us right there. They do sort of tell us d theta dt. We're going to have to do a little work on it there. But it actually is constant. They say the crankshaft rotates counterclockwise at a constant rate of 200 revolutions per minute. So that is the rate at which the angle is changing, right? We're going to have to do a little work on it because they gave it to us in revolutions per minute here. But d theta dt is 200 revolutions per minute. X is changing, theta is changing for this. We need to find, we did talk about that, we need to find dx dt. We need the speed of the piston, or velocity of the piston, when theta equals pi over 3. Okay, everybody okay here? All right, so the good news is although this is a complicated equation, we have a lot of constants to plug in. So A is 7, so we've got 7 squared equals x squared plus C is 3, so we got 3 squared, minus 2x times C is 3, so that goes here, cosine of theta. And I would like to clean that up just a little bit, so we got 49 equals x squared plus 9 minus 6x cosine of theta. We only have our 2 variables in this equation. We got an x and a theta. There's not a third variable because we have replaced all the other ones with constants here. So we don't have to do step 4 where we change it. And so we want to take the derivative. I gave us a little more space here because the derivative is not quite as easy as it has been on the other problems. We really haven't seen very difficult derivatives so far. That part's not been the difficult part of these problems. We got a little bit harder derivative here. 49, what's the derivative of 49? 0. Derivative of x squared, 2x, dx, dt. Definitely not the hard part of the derivative, right? What's the derivative of 9? 0. That goes away. I'm not going to write anything there. Now I've got negative 6x times cosine theta. What do I have to use to take that derivative? Product rule. So I'm going to treat it like that negative goes with the 6x and the cosine theta is here. You also could just keep the negative out front and keep stuff in parentheses. You can do it either way. There. So I'm going to have negative 6x times the derivative of cosine theta. What is the derivative of cosine theta? Negative sine of theta plus cosine theta times the oh, I've messed up. Cosine's okay. That's not where I messed up. I messed up here. Parentheses wouldn't hurt to keep it from being confusing, but I had a dot there for multiplication, so it was okay. D theta dt. I took the derivative of something with a theta, and I forgot my d theta dt. So now I've got a plus sign. I've got cosine of theta times the derivative of negative 6x, which is just negative 6, but dx dt needs to go there. So there's not much you can do to clean it up, but let's clean it up a little bit. I'm going to have 2x dx dt plus 6x sine theta d theta dt plus, nope, minus 6 cosine theta dx dt. And let's leave it at that right now, right? In this case. So I am trying to find dx dt. So I've got 2 of them, but hopefully I'll be able to plug in some numbers so that I won't have to, so I can combine those later, right? So I'm trying to find dx dt. That does not get replaced. I know theta is pi over 3, so I got a number to plug in there. I sort of know d theta dt. Sort of. But how did I measure my angle for theta? That pi over 3, what are we assuming that's measured in? Radians. So d theta dt needs to be in radians per minute, I think is what we're looking at here. Did they give us d theta dt in radians per minute? They gave us d theta dt in revolutions per minute. This is not that hard of a switch, though. Okay, so 1 revolution is how many radians? We go all the way around. How many radians? 2 pi, right? So if I've got 200 revolutions per minute and I want to change it to radians per minute, I just need to multiply by 2 pi, right? So my d theta dt is going to be 200 revolutions per minute times 2 pi radians. I will get 400 pi radians per minute. So your angles and your, whatever you're measuring has to be in the same units. This would be the same case, like, for example, if they had given us the length in inches, but then the x dt we did in feet per, that wouldn't work, right? You have to have inches per minute as your rate there. They have to match. So now they match. So now I do have something that I can plug in right here for my d theta dt. We're just going to have to add another day to relate rates. It's the only way it's going to be possible to do this right here. We're not getting to see today at all. Okay, so we've got this. What's the only thing we're missing? X. So I need X. So right here, x right there is what I need. So much like our Pythagorean theorem problems, we need to plug this back in like to the original. We didn't think like we had to go a squared plus b squared equals c squared and find what we were looking for, right? But it's law of cosines, which you've never done, which means we need to walk through this pretty slowly, right? So let's think of what at this moment, here's what the picture looks like. At this moment in time, this angle is pi over 3. The crankshaft is 3. The connecting rod is 7. This side right here is x. That's what we need to find. So, our law of cosines is, I'm going to write it out like with the A's, B's, and C's, and then see how, so like just general formula, A squared equals B squared plus C squared minus 2BC cosine of A. In this case, A has to be the pi over 3. It's got to be the angle that we know, right? Which makes this side right here A. It really does not matter which side is B and which side is C, right? Those you could do either one as B and C because it doesn't depend on the angle. But the angle you know has to be A, so the side across from that has to be lowercase a. So when we plug in what we know, we have 7 squared equals, our B is 3 squared. Our C, we don't know. I'm going to put the X right there. Minus 2. B is 3. C is X cosine of pi over 3. Okay, we can solve this. Since you've never done a law of cosines problem, this is really like getting out of control. If you had done one before, it would still not be an easy problem, but it would be less confusing. So this is 49. This is 9. We got an x squared. We got 6x. And we can find cosine of pi over 3. Right? Unit circle. Pi over 3's right here. Cosine is your x coordinate. What is cosine of pi over 3? 1/2. Ooh, that feels better, doesn't it? Now, look at this. All right, so we got 49 equals 9 plus x squared minus 3x. What type of equation are we down to now? What type? What? It's a polynomial, specifically what type of polynomial? A quadratic. How do we solve quadratics? Set them equal to 0, and then factor if you can. If you can't, you could do quadratic formula or complete square, right? So let's move everything to one side. So I'm going to actually subtract that 49 right here, and I'm going to write these in order. So I'm going to have x squared minus 3x minus 40. And again, here's where you see this is definitely a textbook problem, I think, because 40 will factor. Like, this will factor right here, right? We can do x minus 8 and x plus 5. In the real world, you probably are not running into things you can factor very often, but you could use quadratic formula to find the answers there. So x equals 8, x equals negative 5. Does it make any sense for x to equal negative 5? No. So we've got x, finally. Whew. We're still not done. Here. Y'all have to go show your parents this problem. Tell them you're ready to design some NASCAR engines right now. 0 equals 2 times 8 dx dt is what we're trying to find, so we're not replacing that. Plus 6 times 8 times sine of pi over 3. D theta dt was 400 pi minus 6 cosine of pi over 3 dx dt. Okay, at this point, this, believe it or not, is a linear equation. Like, it's just like theoretically an equation that a Math 1 kid could solve with a calculator, obviously. But it's just a matter of getting the dx dt's together and getting that by itself, right? So we got 16 dx dt plus 48. Sine of pi over 3 is square root of 3 over 2. And then we got 400 pi minus cosine of pi over 3, we just said was 1/2. So that's going to be negative 3 dx dt. Now, we could do all of this without a calculator, but I'm not going to make us. We're going to put these two things right here together. So we will get 0 equals 13 dx dt plus, and then I'm going to just jump over here and type this other stuff into Desmos. Since we've already spent 20 minutes on this problem. 48 square root of 3 over 2 times 400 pi is going to give us this 52,237. 52,237.4216. Now you just need to move that over to the other side, so you get negative 52237.4216 equals 13 dx dt. You can divide by 13, and we take this number and divide by 13, and we are going to get 4,018.263. This is dx dt. X was measured in minutes. No, time is. X was measured in inches. Time was measured in minutes. So at that moment, oh, and I've lost my negative. At this point, at theta equal pi over 3, that is going to be a negative velocity because the piston is moving back down there. So it's moving to the left in this case. So, and at every instance, it's different, right? So, it's kind of wild. I think this stuff is cool. I also think it's difficult. But, think about applying this like at a higher level. You're designing a, engine for, an F1 car. I'm sure they cannot finish their homework in 30 minutes. It's taken long periods of time for them to analyze everything. So, while it problems as well. This is not the same as the ladder falling on somebody's head. These, I would love to see a similar problem in a different context, because these seem made up. Like I don't know why anybody cares sort of problem, right? So I would love to see these in a different context. I need to look for one that would be in a more realistic context where you might care. Even still, even if I change the context, even if Jeff right here is running away from prison and this is the spotlight they're trying to like catch him with, you know, still doesn't really make sense why we care about shadow. They give these problems a lot, so we do need to definitely look at these. So a light pole is 20 feet tall. Jeff is 6 feet tall. He is walking away from a light pole at a rate of 3 feet per second. At what rate is his shadow lengthening when he is 10 feet away from the base of the pole? Okay, so the light pole, the light is dark, the light is the source of the shadow, right? So like what's happening is the light is shining here, and Jeff is blocking part of that light. So like right here at the end, everything's lit up. But from Jeff's feet to that point right there, Jeff's shadow is blocking out the light on the ground. Or well, Jeff is blocking out the light, which is causing the shadow on the ground. So what is going to happen as Jeff walks away? What happens to his shadow? So think about it think about Jeff being way, like Jeff's over here, way far away from the base. So you got like a shorter angle right here. So the further Jeff walks away from that light, his shadow should get longer. Think about your shadows like during the day. The sun's your source of light in that case. So at like 12 o'clock, when the sun's over your head, you have no shadow, right? So that would be like Jeff standing right under the light pole. You wouldn't really have a shadow. But at, early morning or late evening, when the sun is at like a lower angle in the sky, you have a longer shadow. So as Jeff walks away from the light pole until he gets far enough that it's not really reaching him anyway, Jeff's shadow is getting longer and longer, right? So we are interested in the rate at which these things are changing in proportion to each other. Why, I don't know, but they're asking us, so we're going to figure it out. We need to write an equation for this situation. These are right triangles, but we're not going to do Pythagorean theorem. Okay? Because do we know anything about the hypotenuse here or care anything about the hypotenuse here? There's potential for some angles because the angle to your light pole is changing, but did they tell us anything about any angles or give us like a rate at which angles are changing? They did not, so we don't want to use trig. What we're going to do here is we're going to use similar triangles because this little triangle right here is going to be proportional to the big triangle on the outside. That has to be true because they have the same angles, right? They both have right angles right here. They both share the same angle here, which means the third angle also has to match as well, right? So we have all the same angles, so these two triangles have to be similar to each other. When we have similar triangles, we can set up a proportion, okay? So that would mean, I'm going to start with the little triangle because it is more simple. That would mean that the vertical piece of that triangle, y, over the horizontal piece of that little triangle, x, has to equal the vertical piece of the big triangle. What's the vertical piece of the big triangle? H, over the horizontal part of the big triangle. What's the horizontal distance on the big triangle? D plus x. Okay, everybody okay there? All right, so we're thinking, this is our vertical, this is our horizontal. Y and x both come from the small triangle. h and d plus x both come from the big triangle. So we've got this set up correctly. There is no reason that the y has to be on top. I could have put the y on bottom, as long as I also flip the second fraction, right? So there's several ways you could set this up. We need to think about what is changing and what is constant. What things are not changing here? What is constant in this? What? Height of the light pole, which is h, that is 20, and that is not changing. What else is not changing? Jeff's height, which is our, what is that? Y, is 6. We also know that Jeff is walking away from the light pole at a rate of 3 feet per second. So what would that be? dd dt. It is the rate at which Jeff's distance from the light pole, which is d, is changing. So dd dt is 3. Now, changing, we got to think of all of our variables. H and y are both constant. X is the length of the shadow. That is changing because as Jeff walks away, his shadow gets longer. And D is also changing because he is walking away, the distance from the pole gets longer. And then we are supposed to find, okay, now this is a little tricky. We are supposed to find, yes, go ahead. We're supposed to find at what rate is his shadow lengthening? So shadow lengthening. What is that going to be in this picture? It's a rate, so it's a d something dt. dx dt. X is his shadow. So we're finding dx dt when Jeff is 10 feet from the base of the pole. What variable is that? D equals 10. Okay, so we are going to plug the numbers that we know into the equation that we came up with here. H is 20, y is 6. So we got 6 over x equals 20 over d plus x. And, I've got these set up because I want us to think about like the steps every time. If you recognize 6 and 20 are constant and plug them in up here and don't want to list it like this, that's fine. This is just trying to help us organize our thoughts. So, if we take the derivative as it is right now, we don't have two variables, so that's good. It's going to be difficult. We can make this much, much, much easier. When we have a proportion, we have two things set up two fractions equal to each other. We can cross multiply. So I could say 6 times d plus x equals 20x. Essentially, you're multiplying by the denominator on either side is what you're doing. You're doing like two steps at once. Well, that looks easier. I could even distribute that 6. So 6d plus 6x equals 20x. Could I simplify this even a little more? I could subtract that 6x. And so 6d equals 14x. This just got easy to take the derivative of, right? So when you have a proportion problem like this, cross multiply it and simplify before you take the derivative. You could take the derivative earlier, but you got quotient rules on both sides and not going to be an easy derivative. Now we have a very simple derivative. So we got 6dd dt equals 14dx dt. And we just need to plug in the dt, which is 3. So 6 times 3 equals 14 dx dt. We got 18 equals 14 dx dt. We're going to divide by 14. And so we are going to get 9 over 7 for our dx dt. That is the length of a shadow, which is measured in feet per time. What was time on this one? Seconds. So feet per second is our answer for that. Didn't even actually need D, right? Because what happens is both things are changing at a constant rate, like a different rate, but like they're not changing at the same rate, but both rates are constant there. All right, so we didn't get to a train problem. You already did 21 last night. Try these others. You can skip one. Okay, so I give you one skip. So you've already done 21. Out of these other 5 right here, do 4 of them. I feel like anything more than 4 of these problems is somewhat unreasonable because they take forever. So.